Namaste, I am JVN Dr. Kiran Yadav. Welcome to the digital class. This class is for B.Sc, B.Ed, PCM second sem and B.Sc second semester. In this lecture, I will discuss about, first I will start with adiabatic wall. What is adiabatic wall? Okay. In the last lecture, I discussed about a formula for work transfer in case of adiabatic process. So I will further continue from that topic. So adiabatic wall, here it should be WALL wall, not well. Okay, so correct it. An adiabatic wall is that wall which cannot heat transfer. Okay, there cannot be any heat transfer through this wall. Okay, so this is an adiabatic wall. This one. Okay, this is our system and this is the surrounding. Okay, so there cannot be any heat transfer from system to surrounding or from surrounding to system. Therefore the value of Q is 0 in case of adiabatic wall. Adiabatic wall can be fixed as well as movable. So this is a system where the walls are fixed. Okay, like we cannot push or move the walls. In here the value of heat transfer is 0, and since the walls are fixed, so the volume of the system is constant, and in case of constant volume, we already know that the work transfer is equal to 0. We have derived this formula earlier, and in next is adiabatic wall can be movable as well. Okay, so here these three walls are adiabatic and fixed, and the fourth wall, this one, it is moving and it is adiabatic also. In this case also the value of Q, heat transfer, is 0, but here the wall is moving, so there can be expansion or compression. So in this case work will not be equal to 0. We will get some particular value of work transfer. So I hope adiabatic wall is clear to you now. Another type of wall is diathermic wall. Diathermic walls are those walls in which there can be heat transfer from system to surrounding or from surrounding to systems. Okay, so these are the formulas of work transfer for different processes for closed system. We have already derived all these formulas, so I have summarized it or summarized them here. This is for isobaric process where pressure is constant. The formula for work transfer is P V2 minus V1. For isochoric process, volume is constant. In that case, the work transfer is 0. For isothermal process, temperature is constant, and the formula for work transfer is E1 V1 ln V2 upon V1. For a polytropic process and reversible adiabatic process, the formula for work transfer is P1 V1 minus P2 V2 upon n minus 1. And in case of adiabatic process, in place of n we use gamma. So this is for adiabatic process and this is for polytropic process. Next important topic is units of the various quantities that we will use. So two important quantities that are widely used in thermodynamics are pressure and work. The unit of pressure, SI unit of pressure, is Newton per meter square, which is also known as Pascal. Here this PA denotes Pascal. The unit of work is Joule or Newton per meter. Okay, so the unit of pressure can be in Pascal or kilopascal or in bar. These are three common units that are used for pressure. 1 kilopascal is equal to 10 is to power 3 Pascal and 1 bar is equal to 10 is to power 5 Pascal. Okay, and work is generally denoted by Joule or kilojoule. Okay, Joule is equal to Newton per meter. Newton into meter is equal to Joule. So to make the units more clear, let us take an example. In case of isobaric process, the formula for work transfer is this. Okay, so here the unit for pressure can be in kilopascal or pascal. Okay, and suppose the sorry, and the volume can be in meter cube, and volume is also represented by meter cube per kg. Okay, so we know the unit for volume is meter cube. The SI unit for volume is meter cube, and if we divide the volume by mass, then we get a new quantity which is denoted by small v, and whose name is specific volume. Here this is not volume cube, this is only volume. Okay, so I make a lot of mistakes, you should correct it. There is only v, not v cube. Okay, so when we divide volume by mass, then it is known as specific volume, and it is denoted by small v. The unit of specific volume is meter cube per kg. Okay, so in many equations, sometimes the volume is represented by meter cube, and in many questions the volume is represented by specific volume. Specific volume means volume is divided by mass and its unit is meter cube per kg. So if pressure is given in pascals and volume is in meter cube, then the unit of work transfer will be joule. If pressure is in kilopascal here and volume is in meter cube, the unit of work will be kilojoule. And if pressure is in pascal and volume is in meter cube per kg, then work will be in joule per kg. If pressure is in kilopascal and volume is in meter cube per kg, then work transfer will be in kilojoule per kg. So you have to see what the limits of pressure and volume are, and depending on that the unit of work transfer will be there. Okay, so I have discussed 4 different cases here. Next, for an ideal gas, we know there is a relation PV is equals to RT, where R is characteristic gas constant. The value of R is R0 upon mu, where R0 is universal gas constant and mu is molecular weight. Okay, so R is basically a constant here, and the value of R0 is 8.314 kilojoule upon kilomole Kelvin. In this equation, if pressure is in pascal and volume is in meter cube per kg, then the units of R and T will be joule per kg Kelvin, and T will be in Kelvin. Okay, if pressure is in kilopascal and volume is in meter cube per kg, then the units for R will be kilojoule per kg Kelvin, and temperature will be in Kelvin. So see, if volume is given in the units of specific volume, that is meter cube per kg, and R is given in units of joule per kg Kelvin, and T is in Kelvin, then the work that you will the pressure that you will obtain will be in pascals. And if the unit of R is given in kilojoule per kg Kelvin, then the pressure that you will obtain will be in kilopascal. Okay. And if temperature is given in degrees Celsius and you need to convert it into Kelvin, then this is the relation: T Kelvin temperature is equal to T degrees Celsius plus 273.15. You can also take this as 273 only. You can neglect the terms after decimal. So if equation, so here I have written the gas equation as PV is equal to RT. Like here I have written this equation as PV is equal to RT. But in many books you may have seen that this equation is written as PV is equal to nRT or PV is equals to mRT sometimes. Okay, uh, if the equation is written in this form, PV is equals to mRT, here volume, here V is volume and its unit is meter cube. Okay, and if we take this m in the left hand side of the equation, it will be in denominator of the equation, so there will be PV by m. And if we take V by m as specific volume, then the equation will reduce to PV is equals to RT. Here V is specific volume and the unit of V is meter cube per kg. Okay, so both these equations are correct. If equation is in this form, then volume is in meter, then the unit of volume is meter cube and this term V is volume. And if the equation is in this form, then this V is a specific volume and the unit of this V is meter cube per kg. When you use specific volume, then in all the formulas you should use specific volume instead of volume. Then work will be in joule per kg or kilojoule per kg. Okay, so if you are using specific volume at one point in some formula, then if there is another volume term at some another place in that formula, then you will not use volume only, you will use specific volume in that case also. Like there are two different volume terms in the same formula and you are using units of volume for the first formula and units of specific volume for the second formula, then your answer will be incorrect. You will have to either use volume throughout the question or specific volume throughout the question. Okay, so be clear about that. And if you are using specific volume, the work will be obtained as joule per kg. Then in case of specific volume, the unit of work will not be joule, it will be joule per kg. Or okay, so this was all about units. If you have any doubts, please mention in the comment section.